positive definite matrix? All right. So, single variable case, we want the second derivative to be positive. In the multivariable case, we need the matrix of second partial derivatives to be positive definite. And that's where that condition came about. And last time I showed how the easy way of showing this in the two variable case. And actually, last time, Floyd, who I notice is not here, asked how you would show that a matrix is positive definite in the general case. And I gave one way. But here's the way that's easier to describe, even though it takes more work. So if I say the three variable case, then this is what we're going to have. Okay. So right now, there's nothing that I told you last time that would tell you how to figure out if this is positive definite or not. So here's what you do. We look at portions of this matrix, starting with the upper left corner. We just take this upper left element, fxx. Then we take the upper left 2 by 2 block that has all these guys in it. And then the next one that has everything. All right? So you look at what are called the principal minors. So H11, that would just be the upper left element, fxx. Then the upper 2 by 2 block, so that's fxx, fxy, fyx, fyy. And then you look at the next, the upper 3 by 3 block. In this example, is everything. Right. But let's suppose you had 10 variables. So you'd have a 1 by 1 block, 2 by 2 block, 3 by 3 block, then you'd go to a 4 by 4 block, and so on. You just keep on going. And if the determinant of every principal minor is positive, the Hessian is positive definite. All right. And in fact, the test that I described for you last time, for the two variable case, does exactly this. So you compute the determinant. That's fxx fyy minus fxy squared. And you want it to be positive. And then if fxx is also positive, well, this is the first minor, this is the second minor. You can confirm that both are positive. The matrix is positive definite, and therefore what you have is a local minimum. So this is another way of looking at the test I gave you last time, in a way that you could try this with the, and it requires knowing how to compute the determinant of the matrix, how to handle the free variable case. And there's an example that's worked out in the notes. Free variables. X squared plus y squared plus z squared plus xy. Right. So then you need the second partial derivatives. So the gradient of f is going to be 2x plus y 2y plus x, and then 2z. So this is fx, fy, fz. So now, let's fill in this matrix of second partial derivatives from what we have here. So what's fxx going to be? What? Yes, it's going to be 2. It's going to be a constant. All right. Fxy, and it's going to be 1. So fyx will also be 1. All right. Fxz, 0. So fx does not depend on z. So that takes care of this and this. Fyy, 2. All right. Fyz, 0. So that's u and u. And fzz is 2. All right. So that is your Hessian. Now it turns out to be that's what it is for any x and y. Only because fxyz is a quadratic function in x, y, and z. But in general, it's going to be this will be functions of x, y, z that you got to evaluate at a particular point. Okay, so you look at the principal minors. So the first one is going to be 2. Okay, that's positive. Then the next one is going to be the upper 2x2 block. So the determinant is going to be 2 times 2 minus 1 times 1. So that's equal to 3. All right, so that's positive also. And then finally, we need to determine the entire matrix. How do you go about doing that? All right.
Do like the top diagonal across and then the next one across. Like you multiply them, and those are going this way is all positive, and then you go backwards for subtraction.
I believe you're describing one way of doing it.
Yeah.
Yeah. There's so many ways. I've forgotten some of them, but yeah, because what you're doing is you're taking all the possible permutations of 1, 2, and 3, and you're multiplying all the entries together, and then the sign of permutation determines it. Another way of doing it, which some of you might have seen, is so you go across the top row. So it's 2, and then you take the matrix you get by deleting the first row and column. That's this. So you take 2 times the determinant of this, which we know how to do because it's 2 by 2. Then you go to the next element, and you change the sign. So minus 1, and then you delete the first row and second column. So then it's 1, 2, 0, 0. Yeah. Plus the third element, then you delete the first row and third column. So that would be 1, 0, 2, 0. And you keep alternating signs as you go across. So we get 2 times 4 minus 1 times 2, and then this is 0. So the determinant of the entire matrix is 6. That's positive, so all are positive. Now, for our purposes, like exam problems and so forth, we'll just look at and for practice problems I put out there, we'll just look at the 2 by 2 case, but I want to show you how the 3 by 3 example, the 3 variable case could be done. Yes? Okay.